to the ITC lunch. I have a few statements that I wanted to make because this week, as many of you know, was quite unusual on a number of fronts. Most important of all was the sexual harassment case against Jeff Marcy at UC Berkeley. And first I wanted to mention that I'm very proud that the leadership of bringing this case to light came from the astronomy department here, in particular John Johnson, Dave Charbonneau, and Sarah Ballard, that used to be a graduate student in our department, led this together with Ruth Murray-Clay, who is currently, she used to be an SAO scientist here and also a senior lecturer of the astronomy department. She's now at UC Santa Barbara. They all brought this case to light. And that's extremely important for a number of reasons. Of course, one reason is that this particular case will not repeat. These incidents will not repeat at Berkeley. So, but more importantly is that it will deter. I have a rule that when I find a mouse or a cockroach in the kitchen at home, I get alarmed because there must be many more out there. And so I think bringing this case to light would deter others from doing that, and that's extremely important. I think in general we should make sure that our nearby environment is safe from harassment, and it's not just sexual harassment, but anything related to ethnicity or other. Promoting diversity is extremely important, and harassment is one of the tools that people that some people use to suppress diversity. And so I think it's extremely important for us to denounce it, and also to, if you hear about incidents in this environment, don't hesitate to let me know, or we have a special administrator here at Harvard University called Kwok Yu, and he is dealing with cases like that. So there are people on campus, there are also ombudspersons here at the CFA, and we should all make an effort to eliminate this from our environment. And as all of you know, as of yesterday, Jeff Marcy resigned from his faculty, he's in the process of resigning from his faculty appointment at UC Berkeley. His photo is not on the website anymore of the department. Another thing that I wanted to mention is that yesterday we had, and this is more on the pleasant side, we had an excellent colloquium by Ed Turner convincing us of the unlikelihood of life, the fact that life should not be taken for granted, that we should feel special, that the probability is extremely small for complex life the way we know it to exist, and the talk is on the web, on YouTube. I was just, I'm mainly worried that people that promote intelligent design would be very happy with Ed's message. On the other hand, it can bring a lot of funding to Princeton. And we will hear from Ed in a minute. The other thing is that we just heard an ITC colloquium by Jason Prochaska from UC Santa Cruz, and he will speak also at this lunch. So first we'll hear from Ed about tidally heated ExoMoons, and then we'll hear from Jason about the Jackpot Nebula. Is that a name or an adjective? And after that, we'll hear from another visitor, John Kormendy from Texas, who will be giving the CFA colloquium later today at 4 p.m. And also tomorrow we'll be giving another talk at the group meeting at 11:15 at the ITC Lounge. And here at lunch, John will talk about secular evolution and the growth of PseudoBulges in these galaxies. And finally, we'll hear from our own Igor Chilingarian over there, who will speak about isolated compact elliptical galaxies stellar systems that run away.
Thank you, Avi. The microphone is showing a battery light, so if it goes off, somebody let me know, but I imagine at least a number of you can hear me talk. I'm Ed Turner from Princeton. As Avi just said, I forgot to put my name on the slide, but these are my students, Marianne Limbach, Nate Peters, and Vera Dobos, and who did most of the work I'll be showing you. What I wanted to talk about, and it was published, what I wanted to tell you about was tidally heated ExoMoons. The best thing about tidally heated ExoMoons, a moment while we switch microphones. Oh, it's falling off anyway. All right, is that better? Okay, so tidally heated ExoMoons have the acronym THEM, which might be the best thing about them. You can look for them, study them, get observing time for them, and so on. And what's sort of exciting about them from the point of view of astrobiology is that they offer the possibility of watery worlds far outside the habitable zone, which would be much easier to directly image than terrestrial-type planets in the habitable zone. And in fact, we can probably do it without TPF. Just to show you one setup slide here, a correlation that remarkably few people are aware of is that for the giant planets in our solar system, if you sum the mass in their satellite systems and their moon systems and plot it against the mass of the planet, this is in Jupiter masses and Earth masses, there's this nice, pretty nice correlation. And those in the exoplanet community will know that we have already found planets or low-mass companions of stars with masses up to, say, 10 Jupiter masses orbiting the primary star at radii of many tens of AUs and even hundreds of AUs. So they're far away from the primary star. And if their satellite systems are similar to the satellite systems in the solar system, which who knows, but not a crazy hypothesis, then if you extrapolate this for a 10 Jupiter mass planet, you get a total mass in the satellite systems of order an Earth mass, or 2/3 of an Earth mass, or something like that. And in some of these systems, most of the mass is in one object, others it's distributed. Now, just to slightly reiterate some of the reasons that we're interested in them is, notice the nice use of the acronym, is that they can plausibly be quite luminous, more luminous than the planet in older systems, because the planet's cooled and they haven't. They're kept hot by tides for gigayears. We see that in our solar system, that some of the tidally heated objects are still hot, long after the formation, billions of years after the formation of the solar system, and that they can be luminous at large separations from the primary. And this reduces or even eliminates the contrast problem that is the normal issue with imaging exoplanets. You don't have to look at 1/10 of an arc second away from something that's 10 billion times brighter. And so we can access them with imaging systems which are available to us or soon will be. And another point I want to emphasize is that tidal heating depends so strongly on the orbital and physical parameters that we don't actually have to extrapolate very much beyond things that we know exist to get very large amounts of tidal heating. And that's a good bit of what the talk will be about. This is standard tidal heating theory developed in the 80s, mostly in the context of studying Io and Europa and the Jovian system. And you can write down the tidal luminosity of an object in terms of the mass of the satellite, the size of the satellite, the eccentricity of its orbit, and the semi-major axis of its orbit And this is measured in units of the Roche limit of the planet. That's why you don't see the mass of the planet here. It's absorbed into the units of the semi-major axis and some bizarre-looking physical constants. And these two very important parameters measure the Q of the planet, like the ringing Q of an oscillator, and the rigidity of the material in it. So these are material properties, if you like, of the planet. And I would call your attention to the fact that these dependencies are extremely steep. That one's not so bad, but most of them are, a power significantly greater than 1, which means you don't have to change much to change the tidal luminosity quite a lot. To give you some sense of that, Eo's surface temperature is the highest, actually, in the outer solar system, beyond the asteroid belt. And it's the third brightest object at around 5 microns in the outer solar system. It outshines all but Jupiter and Saturn. If you just took the Galilean satellite system and put it in orbit around Neptune, scaling the semi-major axes to the Roche radius of Neptune relative to Jupiter, Io would be much brighter than Neptune is at thermal infrared wavelengths. If we put the Earth in Eo's orbit, something that's significantly bigger and more massive, it would be the brightest object in the outer solar system. Or if we just moved Io twice as close, it's a little over 6 Roche radii out, if we moved it into 3 or so, it would be the brightest object in the outer solar system, according to this naive theory. This is the punchlines of these papers. Basically, you look in the papers for the calculation. This is a JWST MIRI. That's one of the instruments on JWST. Detection limits for a star 3 parsecs away and a 10,000 second integration in each of the bands of JWST. And what you can see is for temperatures are hundreds of thousands of degrees and objects that are the size of the Earth, you just detect it in many bands. And if you integrate it a bit longer, you could even see a cool object at 300 degrees Kelvin, the size of Io. And, for some Earth-like object at around 300 degrees K, in other words, a world that would be suitable for water to have on it, you could begin to detect it with JWST, independent of how far it was from the star, because the heat is coming from tides. And you could recognize these objects pretty well. They would be faint sources, but all you have to do is have some sort of color or spectral temperature. The distance, so you would know the luminosity, and so you could just work out, how big it had to be at that temperature to be that bright, and you'd get some little object. You would know it wasn't a distant background star. They would also be way too hot to be heated by stellar light. They'd very likely be variable, because tidal heat almost always comes out anisotropically on the surface. There's hot spots, geological, volcanoes and things. Every tidally heated object we're aware of does that. So as they rotate and flare up, you would see a lot of variability. The closest in planet moons will be the brightest, and so they'll have a fair chance of having eclipses, of going behind the planet. Now, I want to tell you a little bit about the second paper, the work with Vera Dobos, was about improving this naive model. The problem with the naive model, everything I showed you up to here, was based on this, is it treats these as a constant, Q and mu. But as you make an object really hot, its material properties, its rigidity, and its Q, its ability to dissipate heat in oscillations, change. And so there's a model called the viscoelastic model of tides, in which Q, for example, is a function of the temperature. So as the object starts to melt, it becomes a less rigid oscillator, and so on. And there's, if you go through the paper, there's a lot of calculations and stuff in this, but basically what is shown here is the amount of tidal heat you get as a function of temperature. Here it's solid, here it's liquid, here it's an object which is solid with pockets of liquid in it, And here it's an object which is liquid with inclusions of solid material. So this is like a gradually melting sequence. And the tidal heating goes like this. The ability of convection, which is what you depend on to transport the heat, follows some curve like this. And just like an interstellar heating curve, there are stable and unstable points. So here's an unstable point. If I make the object a little hotter, then its ability to transport heat goes down, and it continues to heat. And here's a stable point where it's the other way around. So if I make it hotter, the tidal heating goes down and it cools back off. And if I make it cooler, the tidal heating goes up. So you can solve equations like this and find, a solution to the combination of putting in the temperature dependence of Q. And this acts as a thermostat. The object tries to find the temperature at which it's starting to melt. And this has the very pleasant implication for astrobiology that icy objects will, over a broad range of physical parameters of the object and of the orbit, will thermostat into something near the melting point of water. They'll be getting slushy or soft. And since, as I've already mentioned, the heating tends to be very non-uniform, if something is sort of at the order of magnitude of the right temperature, or around the temperature of melting water, there'll be places where it's hotter, places where it's cooler, and so on. And so you'll have water or melted ice at a range of temperatures. The importance of this effect is illustrated. Just look at the solid curves for now, or just look at the solid curves. The naive model is shown here in green. So between 0 and 100 C, the freezing and melting points, this is fixing the density. This is the radius of the object and the eccentricity. We've fixed some semi-major axis too. So you can see the what you might call tidal habitable zone here is pretty narrow in this parameter space. That's the other side of the steep dependences I pointed out. You don't have to, if you have something at the right temperature, you change it a little bit and it either gets too hot or too cold. So this is quite a narrow regime. If you put in the viscoelastic model, which is not something we developed, it's a standard model of tidal heating, you get this much broader range of parameters shown between the red lines. That's the thermostat in action. And it helps on both the cold and hot end of things. So this
brought up public in late 2000s. We automatically downloaded HEC images of central regions of galaxy clusters, analyzed them locally, ran as extractor basically, collected all the candidate objects that we were interested in that were dense and small, and then went back to NED or SDSS to look for redshifts. We immediately discovered 55 candidates in 23 able clusters, and 14 of them were confirmed right away from published redshifts. Then we observed a few more with the Russian 6-meter telescope, and this allowed us to extend an initial sample of 7 to 21. And this is to demonstrate you on this typical plot. So this is an HST image with isocontour plots on top of it for the cluster able 397. There's a central CD and 2 compact galaxies, and one of them seems to have something looking like a tidal tail. And there's a plots where you have absolute magnitude on the x-axis, and on y-axis here you have the surface brightness, the mean surface brightness. And dwarfs and giants are shown in green and orange, and here there was a huge gap in the parameter space, and we filled this gap. There's galaxies, of course, and they're smaller. They have higher velocity dispersions because they're dynamically hotter. But also they have higher metallicity than what you would expect and than what you observe in dwarfs. So the scenario of their formation was tidal stripping of more massive progenitors, and we indeed ran simulations of a Milky Way-sized galaxy that we dropped onto M87. And after less than 1 billion years, we have a very small remnant orbiting this one, and the rest of the stars are spread around in the form of an intracluster light, or they are created onto M87. They have higher stellar densities, they often have higher metallicities, all local compact elliptical that we know where we can resolve from the ground and have long slit or IFU spectra. They all rotate, and 3 have measured central black hole masses. All this is compatible with the tidal stripping scenario of massive progenitors. However, in 2013, there was a discovery of an isolated compact elliptical by Huxor et al. And all properties seems to be the same, so it was dense, metal-rich, compact, old, but there was no evident host galaxy, so there was nobody that was able to produce the tidal stripping. So we thought that it would be interesting to look for galaxies like M32 in all possible types of environments. And we went to wide field surveys that are available in the virtual observatory. We went to SDSS, Galaxy, and UKIDS. We took the master sample of galaxy spectra from SDSS. We limited ourselves to low redshifts where we could see at least something at this luminosity range. I'm talking about luminosities corresponding to stellar masses 10 to the 9, a few times 10 to the 9. So they're really small galaxies, and they go beyond the limit of Sloan if you go further than redshift 0.07. Then we ended up with something that we didn't expect. When you combine Sloan with Galaxy, instead of seeing the classical red sequence, here you have the absolute magnitude of a galaxy versus color in the optical. If you add the third axis, which is near UV minus R, you discover that all galaxies that are non-AGNs, they actually reside on a very thin surface, which is a few hundreds of a magnitude in color. So the red sequence, it's on the tip of this surface. All ellipticals, they reside here, and some spirals as well. All the star-forming galaxies are here. But what was interesting is that compact ellipticals happen to be outliers, among 2%. I described this result a couple of years ago here at the ITC Luncheon. Then we worked out new selection criteria. We just computed this surface, and we tried to look for objects which were on top, which were dynamically hot, which were old, and non-star forming. And then we ended up with this. This is an all-sky plot. Stars are known compact ellipticals, and dots are new compact ellipticals. We found 200 of them. And this is a diagram showing them all of them sorted by redshift. So you see they are almost unresolved. And indeed they're distributed uniformly in redshift. And they represent among about 0.5% of all dwarf galaxies in this luminosity range. So here you're limited by completeness on the left and by Sloan selection on the left and by completeness on the right. We found more tidal tails, which are known to be short-living. So this was another argument towards the tidal stripping scenario. However, when we tried to analyze the environment, we realized that 11 of them were isolated. And this made us think about it. If you try to look at age versus metallicity plot for compact elliptical galaxies, and you plot all cluster and group C as dots and isolated galaxies as stars, here you would see that they actually do not differ from each other. However, the color coding here reflects the absolute magnitude of a galaxy. So you see that they're very different from giant galaxies, from normal ellipticals in the same stellar population, for the same stellar population parameters. You need much higher stellar mass for a normal galaxy to be that metal rich. Okay, 70% and more were living in groups with over 10 galaxies in SDSS, and properties of groups and cluster Cs were fully consistent with the classical tidal stripping scenario. Then the question is how to form the isolated one. Can we get away with this tidal stripping, or we have to invent something else? And then we came back to the paper written by Laura Salas and I in 2007 that was called Cosmic Ménage à Trois. That's really the title of the paper. And so it was actually describing the three-body encounters in the local group that put satellites in very extended orbits, up to 3 megaparsecs away from the Milky Way. And this is what is called caustic diagram, where you have projected distance versus radial velocity difference, and those lines, they correspond to more or less to the escape velocity at this distance. Of course, we have 1 or 2 Cs per cluster, so we cannot draw any conclusions from a single cluster. However, if we plot all the clusters with detected compact ellipticals in the same scale, so we renormalize radial velocity differences and renormalize effective or half mass radii or R20, whatever, R200, I mean, then we can get some statistics. And galaxies which are outside the caustics, they are either infalling for the first time on the clusters, or they're on the edge of the gravitational stability, so they're almost running away. And we indeed found 4 of those galaxies that turned to be runaway galaxies. And this was the solution that we proposed. Interestingly, that we were able to do the back-of-the-envelope probability estimate of how you can eject a galaxy in a 3-body encounter. And if you take the typical lifetime of 2 billion years and a typical semi-major axis of 120 kiloparsecs, it refers to one of the plots I showed, and think that according to modern cosmological simulation, a CD experienced 3 to 4 major mergers on almost radial orbits in 4 billion years, you would end up with 6 to 8% probability of a C to be ejected from the system. And this is exactly the number we get for the number of compact ellipticals in isolation that we found. So, summary, that those objects are not rare anymore. They exist in all types of environments, although they prefer dense regions. And all of them were tidally stripped in the past, and those that we see in isolation, they just left their host systems by the means of 3-body encounters. And we expect to see a lot of free-floating global clusters, like one found by Nelson Caldwell near M87. Thank you.
Questions for Igor? Looks like everything was clear and
Everybody's tired.
Congratulations on the science paper. Thank you all for coming.
Your talk announcement came so late and I fixed up other things.
Well, it's a brief visit. I was pretty tied up for most of the time as usual, I'll be back.
Oh, I read the abstract of your talk, of course. It's a good
If you have any enough interest in it at the time, I guess it's on YouTube.
Yeah, they recorded it. Yes, I will be playing it at some point.
If you ever, we encourage you to watch it. If you watch it, I'd be interested in any well, estimating how long it lasts is not so easy.
Thank you, sir. Thank you.
That helps a lot. Because even if it's not more than one, who's got so on it.
So the thermostat depends on
It just says that if you have a moon, that the tidal heat is going up or down, whatever it is, the orbit or the moon, to put it somewhere near the melting of the Waaaay. Because if it starts to freeze, it starts to dissipate more.
You're fine. You're talking about
Yeah, asleep and talking.
over here.
He does that to me once in a while too.